Alright, in this video I'll be talking about Pade approximations. And you've probably already worked with Taylor series or Maclaurin series to approximate functions like sine of x, or e to the x, or even the natural log of x plus 1. And these series pretty much expand a function into a polynomial, like let's say whether it is x minus whatever, and then x plus dot dot dot, and as well as the natural log being something like x plus dot dot dot, right? We've seen how Taylor series and Maclaurin series help us express our expression of our function, like sine of x, e to the x, and ln of x plus 1, as a polynomial function. And it's basically a sum of powers of x, and we know that by the Taylor series or Maclaurin series, mainly the Taylor of x, is pretty much equal to the sum from infinity and n equals 1 of the function's derivative and x minus a, where a is pretty much the centered point and the n is the degree, all over n factorial. And this is generally the main idea of the Taylor series, and this tells us that we can express any function we want as a polynomial. And Taylor series are very useful for smooth functions near a specific point, like whether it is at 0 or 1 or 2. And the main issue with Taylor series and Maclaurin series is that they fall apart when you try to go further out towards infinity, or pretty much for any big number. And they are very troublesome when you try to deal with tricky behavior like vertical asymptotes, and that's pretty much where Pade approximations come in. Instead of a polynomial, the Pade approximation of a function f of x is basically expressed as a ratio of two polynomials. So basically something like a0 plus a1x plus a2x squared plus so on, up until am times x to the power of m. And it is divided by 1 plus b0 x, or actually I'll just say b1x to make it simple, b1x plus b2x squared, and so on, up until bn times x to the n. And why is this any better? And the reason this is better is because the ratio of polynomials can capture things like asymptotes, rapid oscillations, and even better approximations with fewer terms. And for example, if we were to say, let's approximate 1 over 1 plus x squared, the Taylor series might work well for values near 0. But like, it fails as x approaches positive or negative infinity. But the Pade approximation, on the other hand, it would still mimic the decay by using a rational expression. So basically, to sum up what we just explained, a Taylor series is pretty much a polynomial approximation, and a Pade approximation is a rational function approximation. And because of that, Pade approximations often give more accurate results using fewer terms, especially when the function you're approximating is a function that doesn't exhibit polynomial behavior. So let's go ahead and look at one or two examples of finding a Pade approximation of a specific function. So let's look at an example. Let's say f of x is equal to e to the x. And we want to basically have a Pade approximation with a degree in the numerator of 2 and a degree in the denominator 1. So you write it as bracket 2 over 1, or 2/1. And this means that if we add the 2 degrees, so we have 2 plus 1, that equals 3. So our Taylor series, we have to compare it to the first term with a cubed term. And we know that the Taylor of e to the x is 1 plus x squared over 2 plus x cubed over 6. So we are only getting a approximation for our Pade approximation using the degree 3 term, meaning that Pade of x, or p of x, is going to be equal to a polynomial that has a degree 2 in the numerator. So we have a0 plus a1x plus a2x squared over, and since our degree is 1 in the denominator, it will just be 1 plus b1x. And the main idea now is that we have to compare this and set equal to p of x. So we would have a0 plus a1x plus a2x squared all over 1 plus b1x is equal to 1 plus x squared over 2 plus x cubed over 6. And we're going to compare and solve a system of equations. So since our highest degree is 3, we only have to look at every term in this expression that gives a highest degree of 3. If we get anything higher, like a 4th degree or 5th degree, we just ignore them because they are basically useless to our Pade approximant. So if we multiply by 1 plus b1x, we're going to have a0 plus a1x plus a2x squared is equal to 1 plus b1x times 1 plus x squared over 2 plus x cubed over 6. And the right side, I'm going to leave the expanding up to you, but we could rewrite it as 1 plus b1x and plus 1/2 plus b1x squared and plus 1 over 6 plus b1 over 2 x cubed. And we're also going to have a b1 x to the 4 over 6, but since we said that our highest degree is supposed to be 3, we just ignore the b1 over 6 times x to the 4. So now we have to relate our coefficients such that we have the left-hand side and the right-hand side equal to each other. So let's go ahead and start with that. So we see that the constant a0 is just equal to 1. So let's just clear this up. So we know that a0 is equal to 1. So we could put that up here. a0 is equal to 1. And now we have a1 and 1 plus b1. So that is a equation we could set up. So we have a1 is equal to 1 plus b1. And we also have 1/2 plus b1. So we have 1/2 plus b1 is equal to a2. So we have this equation right here. And from our cubic term, we have b1 over 2 plus 1 over 6 has to be equal to 0 because on the left-hand side, there is no cube term. So if we solve for b1, we're going to have b1 plus 1 over 3 is equal to 0, thus giving us b1 is equal to negative 1 over 3. And we thought we could find a1 and a2. So we're going to have that a1 is equal to 1 minus 1/3, which is just 2/3. So we found a1 is equal to 2/3. And a2 is 1/2 minus 1/3, which we will have that it is 3 minus 2 over 6, which is just 1 over 6. So then we have that a2 is equal to 1 over 6. And we also know that b1 is equal to negative 1/3. So we could finally make our Pade approximation. And we could say that by replacing everything that we have, a0, a1, and a2, and b1 as well, we're going to have that it is, the denominator is 1 minus 1/3 times x. And a1 is 2/3, and a0 is 1, and a2 is equal to 1/6. So let me just label each function as a yellow, like Taylor, and a Pade will be pink. So we have pretty much our 3 functions labeled specifically. So if we look at the graphs for e to the x, we know that it is going to look like this. And the Taylor series for that is going to look something like this. So we have, and it will overpower because of the x cubed. So it will just basically be just under e to the x. So that is a rough sketch. But finally, if we were to compare our Pade, we would have that it looks something like this. So we would have that it starts here, and then exhibits the same behavior of e to the x, but it gets extremely asymptotic at the behavior for x is equal to, since there's an asymptote at, let's say, x equals 3. So there's going to be an asymptote somewhere around here for the Pade approximation. Meaning that our Pade looks much more of a better approximation for values, let's say, like between -1 and 2, since they basically are almost exactly identical. And you can also check it on Desmos or GeoGebra or any type of graphing calculator, so you can see that the Pade approximation exhibits a better approximation than the Taylor series. And this is just a polynomial with a degree 2 and a degree 1, meaning that the numerator has a quadratic and the denominator has a linear function. So basically by that we see that our Pade approximation is going to get better as we increase the degrees of our expressions. But that means that we have to calculate much more longer expressions of our Taylor series, which are going to be something like x to the 4 over 4 factorial plus x to the 5 over 5 factorial, and so on. And you would get extremely large numbers for the numerator and denominator that would basically capture all of the behavior for our Pade approximation. So that's just the example for e to the x, and it's fairly a straightforward example. And we see that Pade approximations capture the behavior of e to the x at some value like -1 and 2 better than the Taylor series would. But of course, it's always going to be a rounding error when we have to calculate the specific value around -1 and 2, because this Pade approximation and this Taylor approximation are not exactly equal to e to the x. So that's just one thing to keep in mind. And finally, we're going to look at the final example. Let's say we're going to look at sine of x. And pretty much we have that this is our function f of x, and we want a Pade approximation with numerator degree 2 and denominator degree 2. So meaning that our degree of our Taylor term has to be a degree equal to 4. So if we were to go ahead and look at our Taylor, which will be in yellow again, we will see that the Taylor of sine is equal to x minus x cubed over 6 plus x to the 5 over 120. And since our highest degree is going to be a degree 4, we have to just ignore the x to the 5. So we have a somewhat okay approximation for the first two terms of our Taylor series, or our Taylor polynomial. And our Pade approximation will basically be a0 plus a1x plus a2x squared over 1 plus b1x plus b2x squared. So now we do what we did in the last example, which is correlate x minus x cubed over 6 equal to this expression where we have to find a1, a0, a2, b1, and b2. So we see that if we multiply, we're going to get a degree 5 as our highest degree. So we ignore the fact that we're going to get a 5th degree and completely just dispose of it and disregard it. So we're going to calculate. So we have a0 plus a1x plus a2x squared is equal to x minus x cubed over 6 times 1 plus b1x plus b2x squared. And we're just going to skip the expanding, so we have a1x plus a2x squared is equal to x and plus b1x squared plus b2 and that will be minus 1/6 x cubed and minus b 1 over 6x to the 4. So we see here that we have a lot of expressions, and we're going to have to make a lot of systems of equations. But it's not all that bad. And the reason I say that is because if we match coefficients, we could immediately see that a0 is equal to 0 because there is no constant term. And for a1, it is just 1. So if a1 is equal to 1 because the x is 1. And what we're going to see is that b1 is going to be equal to 0. So b1 is equal to 0. And that means that a2 is equal to B1, which we know that that is 0, so A2 is also equal to 0. And finally, we have B2 minus 1/6, and that is just going to be equal to 0, so B2 is equal to 1 over 6. So we finally found our values. B2 is equal to 1 over 6. So we basically have everything that we need. And basically now that we have A1, A0, and A2, we could express our Pade as everything if we plug it in. So we would have that A0 is equal to 0, which that will be removed in a little bit, and A1 is equal to 1, so that just stays as X, and A2 is 0, so that goes away as well, and B1 is equal to 0, and B2 is equal to 1 over 6. So that means that our Pade approximation is simply X over 1 plus 1 over 6x squared. So, of course, if we were to go ahead and look at the graphs again, we would see that our function for sine, it would oscillate forever, since it is a periodic function. And our Taylor approximation will look something like this, approximately. And our Pade approximation would look something like, let's say, something like this. And that is just a rough sketch. So overall, Pade approximations are fairly good to approximate for very small values, and they are extremely better than Taylor series. And these two are pretty much fairly decent examples of why Pade approximations are better than Taylor series in some aspects, because of the fact that we are able to calculate decent values for our Pade approximation than we would for our Taylor series. And yeah, that's just a main idea on what Pade approximations are and how to find a Pade approximation. So hopefully that was straightforward and clear to understand, and I hope to catch you in the next one. So yeah, bye bye.